Okay, my friends, big claim today. I know how gravity works, and I can show you the actual particle that is responsible for the gravity, and that is it right there. The black ball is the black ball of gravity. Now, what is the white balls? The white balls are the white balls of energy. This is your weak force, and this is your strong force. And they are glued together like bar magnets when they are in the photon shape here. This is just ready to concuss. That's why you see it in this shape. I'm going to show you the red ones, and then I will explain to you precisely why the black is responsible for gravity. And here is electron flood theory. In 1 second, you will understand everything there is to know about particle physics. 100% of the universe is made of these particles right here. That's an electron. Now, you've always heard electrons just negative. No, it's not. That is what we would consider the negative real power portion, which is normally white. Now, that black ball is gravity. It's the weak force. It has no energy. It only has attractiveness. No energy when it concusses. This explodes like an atomic bomb. Together they make photons, just as I showed you here. That's the photon. You see it? That's the photon. Now, we even see spikes on this one because energy, anytime you have something bashing into something, you're going to get a glow. This is beginning to glow. In a second, it'll turn just into a blurriness so you won't hardly believe. And you'll see it. I will show it to you. Now, so what do we have? We have the basic particle is this. This is, as far as I know, the smallest stable particle, because you can see we can separate that and we will end up with this right here when we impact. These will glow like just complete glow of white, and the black balls just roll away. And as it approaches that concussive separation, it is back to back little particles like that, just like this. This is how I describe it coming into the Venturi. Now, we're going to see what the red ones are. The red ones are the same as the green, it's just that it's a different frequency, which means it's a different concussive value. The green concusses much further out than the red. The red concusses quite early as it comes out of the Venturi. Okay, this is a brief description of how this happens. A red pulse laser, very inexpensive construction laser actually. It's going boop, 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 boop. Well, these are actually particles coming out. The particles I showed you, and we will see again in a second. And those particles come out of here at a regular, very normal rate, and then all of a sudden, as they approach this Venturi, they accelerate. We see them accelerate. We see the particle come and separate itself from the wave. It's getting ahead of the wave, actually, is all it is. And then when it hits the Venturi, it has to crush into the slit of the Venturi like an airplane wing. And they are balls of energy that crush. The white comes out like unbelievable, and the black balls just roll away, as I've been saying, just as exactly what I said. And here's what they look like as they approach the Venturi. You don't see any real definition to them. Then as they start to concuss, they get a little brighter, then a little brighter, and then they explode into the Venturi. And they begin to glow, and the glowier and glowier, and then buzz-a-boom. Now, let's look at it in some macro detail. Alright, here's what's going on here. We're getting the wave going through, and it's never going to go any faster than this, except until we hit the Venturi. Now, we see everything looking red here, and we see all these particles glowing red out here. Why are they glowing red? Well, these are electrons. Literally, these are electrons that are the warm particles in the air. If this was freezing cold air, you would see less of these particles. And this can easily be proven. If it was freezing cold air, you have less particles in the air. Heat is nothing more than extra electrons. So we have a lot of extra electrons here. And they are glowing because this boom, 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 it's everything out front has to concuss to some degree. As this approaches, it's making everything else glow. That's why this is the glowiest glow. Anytime you see a glowiest glow, it means the hardiest hard that's getting hit. So this is getting hit harder than back here yet. All right? Now, these are glowy, are the glowiest glower ones are getting hit harder than the furthest out ones. Now, let's look at what happens as it hits the Venturi. And then we will actually see the particle. And once again, this is what's happening. The laser, which we just saw up to here. Now we're going to see what happens when we use a Venturi. And you're going to see something that's going to say Einstein was wrong. And I'm sorry, I'm not trying to put anybody down. I'm just saying this is new research that needs to be looked at. Alright, so we saw up to here was just regular waves. Now all of a sudden what do we have? Well, we have a Venturi down here. Remember, here it is. Here's exactly what we got. So there's two drums of metal here, forcing these balls of magnetism which surround this particle. And they are huge, as you can see, balls of magnetism. They have to crush down into here. And the ball, this is the particle. Exactly like that particle, exactly like this. It's starting to glow. The white part is where you have the white and then you have the black. The black's doing nothing right now, and it never does anything. The white part is starting to glow. It's saying, whoa, you're pushing back, you're pushing back, you're pushing back. Oh, see these? That's the glowiest glow. That's the front of the wave of the particle. Anytime you're out in the front, you are in the glowiest glow. That starts to pull ahead out away from the wave. It's going too fast for the wave. So obviously it's accelerating. There's no question it's accelerating. Now, what happens here? And I mean, if you can't see that, I don't know. There's nothing really more to talk about. Now, the particle is obviously starting to get energetic. That's what energy is. When you see glow, that means energy. Energy means push to shove. I'm pushing you, you're shoving back. Push, push, and the harder I push you, the harder you push back, the glower you will glow. So as close as to that Venturi as we're going to get over here, it starts to get real glowy. And the black part of this actually separates from the white part, and only the white part is here, and the black part, as you will see, is everywhere around. Now let's look at that a little closer. But remember, anytime you see a glow, that's the hardest hitting part. You see all these particles in the air, they're glowing? Well, they're glowing because everything here is moving forward, has to be concussed. Now, this is a particle right here. It's a particle right there. Because this is the thing in front of it that's getting bashed. And this is the particles stacking up behind themselves. These are particles here. There's probably, well, of course, there's one right here, one right here, one right here, one right here, like that. But they are bashing into particles that are coming back at them now. Because look at this. This is the reverse shock wave. You see this way out here? You see that? I hope you can see that. That is the reverse shock wave. And you say, well, how does that happen? Well, every time a wave compacts, and bam, bam, it's boom, 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 it's shooting back just like it's hitting. Only it's shooting back now harder than it's hitting, because our original wave was only like this big. This wave is, look at the size of this puppy. You see the arc on that wave? When we started, we only had a little bit bigger than this. We might have had like this. But this coming back is like fills the whole room. So we have created a higher voltage. Anytime you increase the energy, you increase the voltage. Now, you're not going to increase the number of particles. Obviously, you only have the same number of particles. But if you can increase the voltage with the same number of particles, then whatever comes out of here is going to have more energy. All right? I mean, it's just the way it is. Voltage is energy, and the higher the voltage, the higher the energy. That's my feeling. And anytime you see something whiter than white, it means as the whiter it gets, the more energy you are seeing. All right, my friends, everything I'm going to show you right now was done with just what I have in my hand. The Samsung Galaxy 3, a Bosch pulsed red laser that does measurements, and these type of little red, red, blue, green lasers. Now, so you can do all of this stuff, and you will see this is all you're going to have to know about physics and energy and electronics and atomic model. It's changed. It's completely changed. And I've known this for 50 years. Now, I didn't know enough to prove it. Well, I knew enough that I thought I could prove it, but I couldn't show it. Now I can show it and prove it at the same time. And I think, well, I'm almost certain now, and if anybody can contest this, I want them to contest it, that the black particles that I will show you are the source of gravity. And there is nothing that exists that is not made of electrons. That means if they say there's protons and neutrons, fine. They're constructed of electrons. There's 1,837 electrons in a proton, so 1,837 of those makes a proton, which is an uneven number. 1,838 of them make a neutron, which is a neutral number. It's just as much of the weak force as there is of the strong force. These will glue together just like this. They will glue together and make photons. Then they will glue together and make atoms, which are these. All right, and they are all different sizes. A little big, 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 big. Now, they all exist inside of either other gases like we have now, or there are other different types of particles within inside of other different solids. There's sulfur, there's magnesium, there's zinc, there's gold, there's all kinds of different things within other solids. And then there is other gases that have smells and all that kind of stuff. Those are different molecules. So, and which different molecules mean they're different little bits and pieces of these. Sometimes they're glued together, sometimes they're broken apart. Sometimes they're isotopes, and they're in the, like, mixed together with other elements to make gases, and all the different things that we smell all day long are made from particles that are like these. And everything here is made from only these right here. All right, this one right here has 1,840 or so, all right, of these particles. In the smallest particle we have, smallest atom we have, which is hydrogen. And then they go up to much bigger. The helium right there, the next biggest one, is already up at 7,350. All right, and then it goes way up from there, way up. So that allows for very elegant chemistry, and it also allows for gravity, and those black balls are what cause gravity. They want to attract to the white particles, and they want to attract to each other. They seem to be bipolar. They have no energy to speak of, but they just like to snuggle up to the white ones, and they apparently don't mind snuggling up to each other, because you saw what they look like. Let's look at it again. This is the best way to look at it. That's the wave coming through. Then it accelerates into the Venturi. We saw the black balls work away from the white particles. Now, this is the black balls and the white balls. And the black balls don't mind being snuggled up to each other this way. They want to be attached to the white balls. And they seem to be able to keep the white balls more or less in check in between themselves. Now, in my mind, anytime there's a white ball, it's going to want to find a black ball, or vice versa. Anytime there's a black ball, it's going to go in search of a white ball. Now, if you go see, there's other particles in here that you can see the whites and the blacks. They are not displaying the architecture of the particle we're seeing here. They just happen to be out of phase or whatever, but they are virtually the same thing. Now, we're seeing black, then white, and then black. At some point, I think sometimes you see black the other way around. I don't know. See white, black, white, black, white, black, see? And these fall into a phase where you can see them very, very nicely. And then the green ones do the same thing too, occasionally. And I'm just saying that that black particle wants to be with the white wants to be with the black, and they can all get together. Now, when they get together, this is the smallest particles that exist. Half of that, which is the electron, in my world, that's the smallest particles that exist. They will always try to find each other, a weak and a strong. And you will get this, one side. Now, when you have light moving, they seem to attach like that. Or that's what we're seeing. And then you saw when they concuss, they separate, the black balls go away, which to me, that's gravity. They come back. You see they want to come back. They hang around the edges and they come back when everybody else slows down. We saw that. So we'll take a look at that one more time. And this, just so you know, this is a very unusual particle. That appears to be a back spinner. And then it did this when it concussed with one of the standard fields. And these are the fields, and you see all the dots? That's the black and white particles, really. Somehow they're still interacting like there's just a solid soup of particles that the center particle is moving through, and it's stimulating those into concussion as it spins around the circle with some kind of polarity. I mean, it has to. What could cause that? What could you think about? What could cause that? I can't think of anything else other than a stimulated polar particle in the center, which I can't really account for, to be perfectly honest with you. There's a lot I'm still working on. But somehow it's stimulating regions distinctly in distances from its center. That's about as close as I can get to explaining it. And I don't know. Now, this one here is being pinched. That's why it's colored. It's being pinched on both sides. I've shown that a couple times too. And you can see the light slows down, speeds up. You see it sped up here after it came through the Venturi, and now it's slowing down here. So we know that the things that Einstein said are not right. Well, you can see it's a particle, you can see it slows up, you can see it speeds down, so it speeds up, slows down. We know it comes through space. It has to get here as the same particle it left as, and then when it concusses with the solar panels and so forth, the particle itself does this. It pushes out, it smashes into a film of photoreactive particles. Let's just call it that way. A photo is this. Reactive, that means they transmit, push electricity out. Now we've been discussing, I was talking with Andy the other day about Andy Marino, who he does the food service labs, but he's he's a technical guy. We were talking about accelerating these light, regular sunlight into a solar panel, and would that increase its ability to conduct electricity? And I mean, it should, because anytime you see brighter, that means you've increased the energy. That's all. Anytime you see it bright, it means it's getting stronger and stronger energy. So coming through the air, it's nowhere near as bright as that. So in my mind, we have increased the voltage of that. This voltage of this is, let's say, 1 volt coming through. These glow just a little bit. Well, once that hits, even coming back, we're turning everything on. And look what it does coming through. So I don't know if I explained it well enough, but the black particles will eventually congeal into a ball, and they will just keep growing bigger and bigger and bigger. And as we go through space and so forth, we're absorbing these particles. They're going to be gluing to our planet and to other particles that are here that are held, already glued, due to the blackness. Those are the black balls of gravity. Okay, my friends, as you know, this is Roger once again from here, which is not able to be said those words anymore because I noticed they shut me down. So I point to that as the source of information that I will present. However, I will also refer to all of mainstream's allegations of how they feel about what they see. And then I will relate it to what we see. And I will document it every single time. And I will show material, substantial evidence every time. And I will always obviously make some form of a conclusion, which may not necessarily be based in absolute fact, and certainly I can be wrong. But these things have to be examined. And I will show you how simple things really are, like gravity. We're going to start off with gravity. And what is gravity? Gravity is nothing more than magnetism. And you say, Roger, how could you say that? And I say, because the Earth is spinning, and it is flowing through the universe, being crushed into whatever is in front of it. Whatever's in front of it, it has to go through and scrub through. Is there anything out there? Well, guess what? Yes. And what is that, Roger? It's light. It's the particles of light we call photons, which are nothing more than back-to-back electrons. They look just like that. And I will show you these particles in the experiments I did with Rod Warren. And these, now I am looking into thin film, and I think we can separate the weak force from the strong force, and I believe that's the weak force right there. That could very well be dark energy. Now, I say it's magnetism to the Earth, and I can literally prove that. If you walk around in the air in a dry room, you will collect static on you. And what is static? Static is not light, because light hits you all the time and warms you up. That's light. This is static. Static is half of one of these. It's an electron. That's all it is. It's an electron, and it collects on you because it is not wanted in the air. But the Earth will take it from you instantly. You touch anything that's grounded to the Earth, bam, ooh, I got a little spark. Well, of course you got a spark, because all of these extra electrons jumped from you into the Earth. Identical to what happens with lightning. Bzzz, poof, electricity, right to the ground. That's why they call ground. It wants electricity. It also wants light, but not like it wants electricity. Electricity 100% wants to go to ground, which is the reactive force is being sucked in. And the black force literally can be pushed away. And that's what's happening right here, I believe. and the colorful, expressive, glowy, reactive portion is being pulled to the earth. Which, if this is right, hubba, hubba, hubba. Now, I'm talking ether. All around the whole thing, it's identical to an electric motor. I understand these things extremely well. Get any electrical engineer, they'll say, yes, that's what's happening. A magnetic field is being forced into a magnetic field on a regular pulse basis in different areas of that magnetic field to force itself or to pull itself. And if you spin it yourself, you create a generator. Spin a motor, it generates electricity. That's what we're doing. We're spinning, creating our own electricity, sucking electrons up through the earth and out. So what are my conclusions? Electrons flow through the center of the earth. Electrons cluster in and out of the poles. Therefore, anytime you see three dots, it's therefore. Anytime you see a regular triangle, it means change. It's okay. So the electrons cluster in and out of the poles. They're being sucked up and around, and then they come back around out here. You see it all the time in the diagrams. So therefore, likely to be warm spots here and there, which Admiral Byrd said there's a hole in here, and I can see where it could very well be. If you look at what happens on the International Space Stations when they spin water, just look it up, spinning water in zero gravity, you'll see what happens. And they add little bits of tea or something in there, and it just looks exactly like the Earth, and it has a tube running right straight through it. And it will be creating electricity on both ends as it spins. Now, gravity is really electron suction. It's sucking the electrons down. Now, it's sucking the strong force part, not the weak force. The weak force is just there for the ride. But the weak force always wants to be with the strong force. Now I'm starting to see that it can really, literally, totally separate itself from the strong force, if this is what I'm saying it's right. And I believe it is right, because if you look at these particles, every one of them has a dot inside of the actual ball of light. We're going to get deep into this in a minute, very deep. But let's just keep going here. And of course, my electron flood theory says that there are only electrons, which are dipoles. They have a positive end and a negative end. And the positive end is this right here. It has no value whatsoever other than to hold on to the negative explosive part. Seen it, shown it. We're going to do it 1,000 times over. So there's only electrons, and one of them is the carrier, and the other one is the power. The power is the white one, the carrier is the black one. All free electrons are ether, and they're everywhere. Every time you have heat, that's an electron pushed into something. That's all. That's all it is. It's an electron pushed into something. When it comes from the sun, that's what I called ether. Now, so all free electrons are ether, and they are everywhere. Everywhere, everywhere, everywhere. In this rock, there is a ton of ether, which is extra electrons. If I put this in a warm place, it would get more and more and more electrons, and it get more and more and more warm. If I put it in the freezer, all the electrons would go to where they were wanted more, and they would get sucked out of here, and it would get cold. That's all it is extra electrons moving in or out. And light is back-to-back electrons like this. Half of this, like that, is an electron. All right, Earth spins its electrons, which are all over the place. We know because we get lightning all the time. Lightning all the time. So they're all over the place in our atmosphere, which is ether, which creates a generator effect. Earth is overcharged. Yeah, that's the problem. That is the bad news, my friend. Earth is overcharged. Okay, my very, very, very good friends. Today I'm going to give you an aptitude test. Now, what is an aptitude test? Well, it means how do you think, really, is like aptitude. In other words, are you more directed towards sciences or arts or poetry or all that kind of stuff? No. I'm not going to say this word anymore. I noticed since I started saying the word again, everything's been shut right down, even on Facebook and everywhere. So this is where we're going to be dealing. This is the place which will be disseminating the information around the world very shortly, because the information we have needs some serious looking into. Now, if you want to become a scientist, you could do it easily. And you could do it basically with most of the things that people have right in their own homes right now. You see that cell phone? That's a Galaxy 3 Samsung. That's what Rod used. And he discovered that he could send laser into the selfie camera and get all these extraordinary images. Now, so that led me to thin film photography, and that's what we're going to be looking at in a moment. This is off the charts. Now, get your book. Remember I told you, get a book, and you write down exactly what you see. And then you will have it preserved, and then you will be able to present it if you had to. And it will show that you were invested and engaged. Now, really, if you want to be really deep into this, you could get a microscope like, I don't know if you can see that over there. You see, that's, I got to be honest with you, I don't use it. The only reason I even took the cover off it so you could see it. I just don't use it. I don't need it. The one I use is this one here, and these are cheap. I don't know what you. This one here, I don't know. I can't remember how much it was a long time ago. But I know they're cheap now. You could plug them right into your laptops or whatever, a little tablet or whatever you have, and you go out in the woods and look at all of the surfaces of these rocks, and you will see the fabric of life and all the things that I've been talking about. So let's get back to the aptitude test. What do you see right there? Or can you see that? Yes, you can. Let's home in on that. Now, we're going to go into this. I'm going to show you a second. I want to give credit to the guy that is doing this thin film photography. But the average person looks at that and says, wow, that's fabulous looking, and then they just go on about their life. I look at it and I start to think, what is going on here? Why are we seeing this black? Separating from all this. What's that all about? It's, oh, that's soap. I say, okay, good. Is that black just transparent now? Or is it just real blackness? And I think it is real blackness. That is what I want somebody to test. I'm not going to do it. But I think somebody could test to see, can you shine light through that blackness and see the light coming through it, or does that blackness obstruct the light? Or does it somehow diminish the light? Or is it just so that it's so thin at the upper layer because it's stretched? Water will, this is the thin film up here. This is the thick film down at the bottom. And water pulls it down. And it all just sort of migrates down. That's why you see different colors. There's different compression zones. And, you know, and so make yourself notes. Think, and plus, what is the air that's in here? Is it just something that is in the air? Could you put carbon dioxide in there, or nitrous oxide, helium? What would it do? What would it do to these colors? And in my, you know, I'm going to tell you what. Let's get a little deeper into this. But then make yourself notes down there. Is the black at the top clear, or is it like paint? I think it's almost like paint. And then if you change the gas, what effect will that have? Water pulls until the thin top layer fails up here. It'll keep pulling down, 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 which compresses the sides in and in and in, which forces more and more black up to the top. That is what I'm saying. Now you take, which is this is the crushing compression zone, is the strongest right up here. It's pulling it down. It's like, yeah, squeezing it in, and I believe it's forcing the black particles to walk away from the white particles. The white particles interact with the incoming light, and you get back that. But the black particles don't send anything back. Now, Are they literally a blockade of particles? If they are, that means they're particles. If it's just empty space there and you can shine a light straight through there and see it, that's a different story. But if you shine a light through there and you can't see it, that's serious. That means they're particles and they're dark, and that's where the dark matter is and the dark energy. Again, make sure you document this stuff that you do. Okay, I'm not going to say anything until this whole video is done and you make your interpretations. And before you listen to my interpretations, you should make your book and then make adjustments to it, if necessary. Maybe you got it better than I do.
When I was working on my high-speed photography setup a while back, I started messing with soap bubbles and films. I was trying to make a system to detect the exact moment a bubble pops for a high-speed photography project, and it actually worked. But along the way, I became entranced by the surprising beauty of these soap bubbles. To me, they kind of look like a vibrant gas giant planet, and I was so excited about this that I posted it to Reddit. But why do soap bubbles appear the way they do? And how come this part of the bubble is completely transparent and doesn't seem to show any reflections at all? Well, we can answer these questions, but first we need to talk a bit about thin film interference. When light strikes the film of a soap bubble, some of that light is reflected off the surface, while the rest is transmitted through the film. Likewise, when the transmitted light hits the backside of the soap film, some of it is again reflected while the remainder is transmitted. The light that is reflected passes back through the first interface and is refracted back out along the angle identical to the first reflection. That's simple enough, but because of the proximity and the coherence of these two rays of light, they can actually interact with one another. The second light wave has to travel a longer distance as compared to the first, and as a result, the two waves may be in or out of phase. However, if they are in phase, there is constructive interference, and that particular color will be enhanced. Thus, whether a certain wavelength or color of light will constructively interfere or not depends in part on the angle of incidence. Here is a glass mask that I had laying around that was once used to make computer chips. On the back side is a very thin film, probably an anti-reflective film, but we'll get back to that. As I rotate it in the light, you can see that the color of the camera sees depends on the angle that is being presented. However, we can also see that the interference will depend on the thickness of the film. To prove this, I created this two-dimensional soap film and hung it vertically. We can clearly see that the color of light being reflected depends on the height of the film. That's because gravity pulls on the fluid in the film, causing it to be thicker at the bottom and thinner at the top. Repeating bands of color appear because the waves will constructively interfere at integer multiples of film thickness. As a result, the thickness of the film can be backtracked and probably look something like this. But why do we see white at the top? Well, in that region, the film is so thin that no single color is constructively interfering with itself, and all wavelengths are making it back to the camera somewhat equally, so we see it as white. But something interesting happens as the film thins even further. In this region, the film reflects no visible light at all. The same is true for the bubbles. As the bubble gets larger and larger, we see that the color is changing because, as we learned, the thickness of the film is getting smaller. Just like the 2D film, it goes from orange to white, and then we see regions where it's completely transparent right before it pops. Here's an even better example with the stationary bubble. We can again see banding as a function of height, changing as time as the fluid is pulled from the top of the bubble to the bottom. And then right there, the bubble has become so thin that no reflections are possible. Look closely, you can actually see the reflections disappearing. Shouldn't we just see white? The reason we don't see white is because there's something I forgot to mention earlier. When a light ray bounces off of an interface, that first ray of light will actually be phase shifted by 180 degrees, or half a wavelength, if the index of refraction of the first material is less than the second. So, when the film is so thin that the extra path length traveled by the second reflection is negligible compared to the wavelength, again, the first reflection will destructively interfere with the second because of the phase shift. So these bald spots, for example, on these bubbles indicate that this portion of the film is probably only about 10 nanometers thick, and it's no wonder they pop shortly after. Likewise, these little black dots are just really thin film rising to the top of heavier, thicker portions of the film that fall. However, I definitely don't understand the dynamics at play here, and perhaps that will have to be saved for another time. These concepts can be applied to practical uses, and most optic systems, for example, have a thin film coating to cancel out certain wavelengths. We also see thin films in nature all of the time. The wings on insects are a great example, but you've probably seen it just on the street on a rainy day. I thought I'd end this video with a few images that I took of some soap bubbles, and now equipped with an understanding of the physics, I think they're even more interesting.
Okay, my friends, draw yourself some interesting pictures and then try to explain these interactions. You're going to see the curve, and you're going to see, well, in the video presentation, you see these moving up. Why is that black ball moving up? Why did the black ones go up? Why don't they drop down? And are they so black that nothing's coming this way either? I believe that's the case. You know, pay it real close attention, and you'll find out.
When I was working on my high-speed photography setup a while back, I started messing with soap bubbles and films.
That somewhere over in this area, I want you to start looking at it and thinking, can light come backwards? I say no. I say you get no reflection this way. This is a dead zone, and I believe in my own mind that is literally what you would have to consider dark energy. That is the particles that were the black particles attached to the white. They've drifted up. All the particles that have energy are drifting down. See them? Those are the particles literally moving down into the energetic region, which is towards the Earth, because the Earth is an attractive force to energy. Earth attracts energy. And the reason it does it is because the spin of the Earth inside the magnetic particles that surround it creates an electric field that flows up through the poles and sucks electrons down. The positive compressive forces of electrons. We know that because they hit the Earth and they warm up the Earth. They hit solar panels. They drive electrons into conduction. Now, if we can do other things, and we're going to be thinking about using a Venturi, how to accelerate them into these solar panels to maybe create a little more efficiency. There's a lot of things we can think about, but I believe these are literally the white balls that normally would be attached to the black balls. Okay, mes amis, if you are here on this site, I pre-assume that you understand that I have fossils of giants and that I claim that geology is biology. So let's look into that. Okay, my wonderful friends, Roger, you know where I am from. A word not well to be spoken, because you get put on a blacklist for speaking against authority. Now, this, as everyone knows, is a giant human hand, DNA certified. And this is a left hand, and you have the same thing running right down here as a tendon, and that's the pad of the hand. And this silver stuff, you see where it's peeling off here, the silver stuff? That's the grip skin. That's the real tough stuff. Now, I have fingertips. This has been DNA tested, and we took it from deep inside, right from the vein. And this is the fingertip, and it's, it's CAT scan DNA tested, certified by Gil Hedley, world famous anatomist, who literally discovered interstitium, and they just acknowledged it in 2015. I worked with him 2013, 2014, when I was trying to understand what was going on here, and this is the first time they could actually see, well, we could see it, and then all of a sudden, next thing we know, they started announcing in 2015 that it was accepted as a new organ. Now, that's a 36-inch wide hand. Right here, the same thing you have here. That's the pad that runs right around. It strips right down here, just like putty. You see that? Now, this was on the surface of the Earth. All right, so these are giants, giant, giant, giants. And I have the fingers, I have knuckles, I have all stuff, and the whole thing is buried out here. I have some parts of the feet, all on the surface, basically, just barely under. Now, what does that mean? It means that the thing was 36-inch wide hand. And that isn't even the big one. Here is the big one, also DNA certified. All right, this was, well, it still is. It's out there. I'm not moving it, obviously. The thing weighs about a bazillion pounds. That is the fingernail. You see that? That's the fingernail. And I mean it is pristine. That is the bone that's in the back of the fingertip. And this is the flesh that ran around the sides of the finger. I mean, it's absolutely flawless. Not only that, the fingertip, fingerprints are also flawless. And I broke one off from the other side. This wrapped right around here like this. Okay? On the other side of this finger. Can you see that? No, you cannot. All right, it wrapped right around the top of that finger like this. This is the grip skin. It gets thicker and thicker as it gets down. You see it's thinner up here on the sides as it comes up to the edge. You don't need that tough. Here's where you need it, way down around the bottom. And guess what's down there? The fingerprints. You see that? Those are literally the fingerprints. Go to any anatomist, anybody that has any understanding of fingerprints, and there they are. And those little dots are the sweat pores in grip skin. No question whatsoever what this is. If an anatomist looked at it like Gill, and he did agree, and that's what it is. It was like this. Now, I just showed, well, I have shown, so I'm not going to do it right now, in the microscope, all the little blood vessels and so forth. The feed, you still has to have some tissue fed with blood up here. Not a lot in the grip skin, because there's not a lot of biology going on in there. It's not a lot of real aqueous, like a lot of fluids running through there. That's same thing on yours. It's, you know, mine is getting old and nasty, but you know, when you're young and it's tough and you're grippy, and it depends on what you're doing for work. If you need it, you'll make calluses. That's the way your body works. It not fully understands everything. And to think that all this just happened by accident is just absolute nonsense. The Big Bang just is crazy. Einstein's, all this stuff is wrong. I'm showing it all. Now, going along this line of thinking, I'm thinking about these giants, and I'm thinking, you know, somehow I got on this thing about badass giants. So I go, here, let me show you. Now, the reason I got all my manuals and stuff in front of me, because I was a badass. I fought everybody. I'm going back through my manuals, and I'm talking conclusions. Well, I want to check this out. I'm not sure about that. I don't believe this for sure. So I did all of this stuff myself to see if all of these conclusions were right. And I found what I thought were errors. And I knew that it was dipoles. Anyway, what I'm getting at is you have to document all the stuff you're doing to understand, because now I'm into the electron flood theory, and we're into dark energy and dark matter and all that. But this just set me off. I want to show you this. All right, here's what it's about. These are 11 badass warriors in history. And so I started reading, because I'm looking for giants. So it says, some days you aren't feeling like you're up for the challenge in front of you, tired, sore, exhausted, beat down, all done. It's just not your day. And I've had those days occasionally. You're feeling like it's time to move on and try something else, admit defeat and back down. No, that's never happened. But that's just your fear talking. In truth, you are much more powerful than you think you are. Well, I don't know about that. The only limits you have are the ones you place on yourself, or silence is placed on you. That's kind of a limiting factor. Now, let's look at this. This is kind of cute. All right, listen to this. This is crazy. To your cool. He was a warrior who lived pre-16th century, before like the 1500 eras, held captive by the Aztecs. So they captured him somehow in some kind of a battle. He integrated himself in with the Aztecs and became part of their clan. So they held him in captivity. But listen to the size of the guy and why he stayed there and so forth. It's kind of funny. Nobody knows why he stayed. Most likely it was for the women. Isn't that why most warriors get sidetracked? Tikul was promoted to commander of the army. So he's a tough guy. And wait, here it is. A job he was really good at. It said that he was so large the other soldiers could not even lift his weapons because they were too heavy. Now, I just showed you a 36-inch wide hand, and then I showed you a fingertip that is 30 inches wide all by itself. And that is not the biggest of all the creatures. And these are on the surface, right on the surface of the earth. So this is not long ago these things were here. I don't care what anybody says, that's just a fact. I attribute it to the Great Flood, but this was 1600 eras, and if this was true, and it was written about a contemporary time, and he was a guy alive at that time, so it's just, to me that's what they're saying. Now, he was really good at being a soldier, and other soldiers couldn't even lift his weapons. He was just that big. Now, when the Aztecs went off to war with the people of his tribe, the Texacal, the young warrior realized he could not fight for the Aztecs. He just couldn't do it. It was against his belief system. He had been living among these Aztecs, nor could he go back to his own people, the Tikal, and fight against the Aztecs who he was just living with. So it was a lose-lose situation for him. So he asked to be given a warrior's death. A lot of these guys choose death before dishonor. Very, it's an admirable thing. Now, he would fight as a gladiator to his death. Now, so a gladiator, he was apparently just fighting other guys that were gladiators, not in a war against them. It doesn't sound like to me. Only it wasn't that easy. Warrior after warrior came to fight him. Maybe his own guys came to fight him. Maybe other guys came to fight him. Somebody seeking glory, apparently. And although he was ready to accept his fate, he was ready to die, and that's what he was looking to do. He wasn't ready to just lay down and be killed. He said, no, you're going to fight until somebody is better than me and kills me. He ended up killing 8 Eagle warriors, wounding 20 other warriors. Now, Eagle warriors were the top of the line killers. And wounding 20 other warriors before he fell to his death. After he died, his heart was cut off by a high priest as a sacrifice to the gods. Now, that's a pretty tough guy. And he was a giant. And this goes on. This is all very good about people that stood up and they did this. They were warriors. They battled against this and that. And so anyway, that's just a little sidetrack. But you got to stick up for yourself. But in this realm we're in now, you don't go out and get your guns and weapons and swords and knives and everything. I mean, not at this point yet. What you want to do is be able to talk against the people that are not paying attention to what they should be. That's my point. And I have all the evidence. And so the point I started with was, I'm going back on even here. Oh, I don't know what I did with it. Maybe I already showed it. Way back here, I was doing all the calculations to prove what they were saying, to see if all of the things that they were talking about were correct. Anyway, and I'm still doing the same thing. And every time I see a conclusion, I can see, I got to check whether this happens, that happens. But all of this stuff, like magnetism, there's 5 types of magnetism. I'm sure you didn't know that. I don't even think they teach that in schools. But it's electron flood theory, is a ferromagnetism and ferrimagnetism, magnetic moments, which means their electrons are locked into a certain position in that molecule. That's a magnetic moment. Now, hot is when you have extra free electrons. So when this thing gets hot, All it is there's extra electrons in here. They want to get out of here. Now, and it will, if this was magnetic, it would stay magnetic even though it was warm. But once it got so hot, it would stop, it would become non-magnetic, and it would not come back to magnetism. I don't believe. And anyway, hot is extra free electrons. Now cold is just pulling electrons back out. So there's no electrons. Extra electrons are what's known as ether. Now ether exists everywhere. It's always has extra electrons. That's what they call a background radiation. They found it's 3 degrees above absolute zero. Everywhere they looked, minimum. Everywhere, 100%. So, because they were trying to look at stars and see how much energy they had, and they expected to see nothing in space, and they got 3% everywhere. So they call that microwave radiation from the Big Bang. Well, it's not. It's the light and the ether from the luminous sources of the universe. And it's pretty much consistent on our Earth. We're seeing 3%. No matter where you tilt that thing and look, because that's where we are now. So that is the ether that exists. So it's not just background radiation. It is the particles that we're scrubbing through, because they're coming through and hitting that radiometer detector, and it's spiking it. But just tiny little bitty pieces. Normally regular light off the charts. But the particles are so far away, it's getting just a taste. Now, 3 degrees above absolute zero only means there's a couple of electrons coming in to warm up the space. If there was no electrons whatsoever, that is absolute zero. And you cannot get to absolute zero. I don't think they have ever, but they get damn close. But you can only extract so many electrons, and then you have just nuclear mass that has just enough electrons in the cloud to cover its bonding potential. And at that point, absolute zero, there's just nothing left that can push anybody around. You put 1 electron in there, you are above absolute zero. And I could show that, and I have shown it in the experiments they did in space. You push 1 electron into a little, it's a little polar looking thing. It has a positive and negative. And when you put it in, it flows through the fluid, and you see the bubbles, bubble, bubble, bubble. And every one of them has a center. And every center, you see that as well in the thin film experiments. There is so much to think about here that is not being considered. Anyway. Then you got the Curie point, which is where you got magnetic moments start to lock. And at any temperature above the Curie point, they lose magnetism because there's too many electrons in there. They won't line up anymore, and then they just go all crazy. See, the fields line up as ether. As the ether leaves, they get magnetic, and you pull that against a bar magnet, and it will polarize them. But if there's too many electrons in there above the Curie point, it just won't polarize. It'll be non-magnetic. Now, different crystal geometry has a change on magnetic properties. Cubic seems to be the more powerful, and that's this one here, and that is exactly what the electrons look like. I think that's the most powerful one. And then we're going to go into this. This is really, really, really cool. It's, I forget what the name of this is. I got to write down a name. I didn't even write. Oh, yes, I did here. Sheeran Effect. Sheeran Effect or something. And you shoot light there, and it creates a reverse Venturi. And then they put it through gases, and it separates, like that's like what a flame would look like. You just see a glowing flame. Once the light comes through that, it separates them back out to the black and white. Absolutely stunning. Stunning. I'm going to show you this stuff. You're going to, well, you'll see it all. But my point is, make yourself some documents. You know, when you do this stuff, like here, I'm going against Einstein. What is he talking about, Einstein? And I'm saying, I can accept this, or yes, no, whatever. Little bits, okay, no problem with that, no problem, no problem. whatever, same number of, I don't know, I have to go through and look at all, but this, make sure that you document yourself. All right, and then you have no reason to be able to not go and speak confidently. But if you don't do something like this, you're going to just be another guy saying, oh, I know what I'm talking about. All right? Document it, be sure you're right. And then I'm going to recommend that, you know how I used to have book clubs? Well, bring your book club. And then you sit down, tonight we're going to do light. Tomorrow we're going to do history. The next day we're going to do something else. The next day we're going to do something else. You're going to have different, you know, I'm interested in everything. So that's, to me, it would all be interesting. And I would want to engage with somebody that was willing to do this to back up their statements. And I have never had anybody do that. Not a single one. Not even my professor. Not even my professors. Same thing happened to other places. Several, as a matter of fact. So, why don't you have bring your book of the month club, or get online and share your document, your text, your videos of what you present, and you give, everybody gets the floor. I'm going to give you, you know, Christine, here's the floor for 10 minutes or whatever. Let's let Christine talk. And then there will be questions, and then there will be interaction. That's learning. You know, I'm too old to get that, and I don't know how to do that stuff. But if somebody would do that, I am perfectly willing to interact. And I have a lot of research. I do. I have a lot of research. And I have a lot of knowledge on this stuff. I'm not bragging. It's just a fact. And it's knowledge that's been overlooked, just because it's unwelcome. And I can understand why. But I also understand that if you're going to be an honest, truthful person, you confront things that are uncomfortable. Let's go with that. Okay, my friends, I have an alternative education plan. They're talking about closing schools, learning online. Absolutely, that's fine. What you should have to do is everybody gets their own book, and they show these online. Here's what I did, and here's, and then, you know, everybody's got video and this and that now. Show your book, and then everybody asks and says, well, why is this happening, and what do you mean by this, and so forth, and you discuss it, and then that is learning. Now, and you could do that online, or you could do it in groups. If you do it in groups, you take one person that's willing to take the chance of taking 20 kids in their house or whatnot, because the kids, they don't get them very often, the infections. And the ones that are getting it are just got antibiotics and stuff. They need to have probiotics. They wouldn't have these issues. We wouldn't even be in this if everybody was taking probiotics. And I have 90,000 people now that are following me, and I have 0 people that have reported being sick that are taking probiotics. 0. So if you have, speak up. All right, now listen to this.
Chicago's mayor says they will provide support to parents who can't afford to stay home, but so far there are few details. As for the nation's largest school district, New York City, it's announced a hybrid plan with a few days a week of in-person instruction, but New York's governor hasn't yet approved that plan.
All right. I think the kids should, they have to start learning, but they have to start learning the right stuff in the first place. So I think this might be a good thing for them to start learning away from mainstream, because I'm going to give you both sides. I will show you both sides, and I know both sides, so don't worry. You can always step up and say, oh, Roger, you know what we're talking about. I say, okay, let's talk. All right, I love you.